Okay, so good morning, everybody. Today we are going to finish the course of stochastic calculus. Okay, and I will use the last session in order to correct the exam of the preceding here. Okay, so let's split my screen. So I remind you that during the previous session we have started to study the Black-Scholes model. Okay. And we have seen several things. So I remind you that in the Black-Scholes model, okay, the way I present it, okay, we have one non-risky asset and one risky asset whose dynamic is given by this stochastic differential equation, and I have here a geometric Brownian motion. Okay, so I have a process for the risky asset that depends on two parameters, b and sigma. B is called the drift and sigma is called the volatility. Okay. And at the end of this session, I will say a few words concerning the way to fix them at the very least for sigma. So if I do this hypothesis for the risky asset, we have proved together in the previous session that in the Black-Scholes model, there exists an equivalent martingale measure that is measure or probability equivalent to the historical probability that make the actualized value of the risky asset a martingale under this new probability. Okay, so we have proved the existence using the Girsanov theorem. And we have also proved the unicity of this equivalent martingale measure, and the unicity is obtained using the martingale representation theorem. Okay, so we have a unique P star star such that ST tilde, the martingale under P star. And P star comes from Girsanov. Okay? So unique P star that is equivalent to the historical probability here. And what is more, and what is nice in the Black-Scholes model is that I perfectly know the dynamic of ST and so of ST tilde under P star. So keep in mind that under P, I have D of ST that is equal to B ST dt plus sigma ST dBt, where here I have a Brownian motion under P, and under P star, I have D of ST that is equal to R ST dt plus sigma ST dWt, where here you have a Brownian motion under P star. So I see that these two equations have the same form. The only thing that is changing, okay, is the fact that the drift parameter B, okay, that is unknown in the case of the historical dynamics, okay, becomes the risk-free rate small r. So it means that my dynamic under P star, okay, what I call my risk-neutral dynamic here, only depend on a single parameter, that is the volatility parameter. I don't have B anymore in this dynamic. Okay, so I have this. And in particular, okay, something that I will also use is the fact that, okay, if I have this, using the integration by part formula, I have D of ST tilde that is given by sigma ST tilde dWt. Okay, so I have a unique equivalent martingale measure, and what is nice is that I know perfectly, okay, what is the dynamic of the risky asset under this new probability. Okay. So I have reminded, okay, in the previous session, what was the definition of a financial strategy and of the associated portfolio with the hypothesis on no friction on the market, okay? And what I have defined, okay, so I have just reminded that in the definition of a financial strategy, I have two integrability conditions to fulfill that are make these two integrals well defined. And I have just said that in the case of the Black-Scholes model, I have two easy conditions on theta 0 and theta t, theta 0 being the quantity of a non-risky asset in my portfolio, theta t being the quantity of risky asset in my portfolio at time t, and I want them to fulfill this integrability condition in order to give sense to these two integrals. So here I have a classical Riemann integral, and in fact here I have two integrals, a Riemann one and a stochastic one. Okay, we have defined in the case of the Black-Scholes model, okay, the strategy we are going to work with that we have called the P-star admissible financial strategy. So P-star admissible financial strategy are strategies that are self-financed, okay? Self-financed strategy, meaning that, okay, I can readjust my portfolio at any time, but I have to respect at any time the budget constraint, okay? And I am P-star admissible, okay, if the associated actualized value for this financial strategy is a square integrable and non-negative martingale under P-star. Okay, so it's the strategy we are going to work with, the good one, okay, the one with good property that will allow us to be able to do what we want to do, that is to price and to hedge. So I have reminded the definition of what is a contingent claim in the case of the Black-Scholes model. Okay, it's just a random variable that is F capital TB measurable, okay? And I impose the square integrability condition with respect to P star here, okay? And it's what I call the contingent claim. And to fix the ID, remind that a contingent claim will just be the payoff of a European type option, let's say, okay? So for example, you can take as an example, this one will be a contingent claim. So you have the payoff of a call option. Here you have the payoff of a put option, but it's not the only thing. Okay, I can consider also what we call a digital option. Okay, something like this, and so on. Okay. So for a contingent claim, okay, we introduce this definition. We say that a contingent claim is P star attainable if it is equal to the final value of a portfolio associated to a strategy that is P star admissible. And what is the meaning of this one is that, okay, using the assets that are present in the market, that are the non-risky and the risky asset, I want to be able to recreate, if you want, to build this contingent claim, but using P-star admissible financial strategy, okay? And in some sense, okay, a contingent claim that will be P-star attainable, we also say P-star replicable, okay, is in some sense an asset that, okay, you can deduce from the assets that are present in the market, okay? And we say that the financial market is P-star complete if all the contingent claims are P-star attainable, meaning that if I can, okay, obtain all the contingent claims of the definition 5.2.2, okay, from P-star admissible financial strategy. And what we have proved together in the previous session was that the Black-Scholes market is P-star complete. And what is more, okay, the value of at time t of any financial strategy that allow to attain this contingent claim, and what I call an aging strategy or an aging portfolio, is given by this, okay? It's very easy to obtain this because, okay, what I use in order to have this, I use the fact that I want to replicate, or I want H to be attained by my strategy. So the final value is given by this one. And I also know, since I work with P star admissible financial strategy, I know that VT tilde, okay, is a martingale under P star. And so if I use both, okay, I can say that VT tilde is equal to the expectation under P star. This notation, E of star, is expectation under the new probability P star, the unique equivalent martingale measure of V capital T tilde given FTB. Let also me remind you that in my situation, okay, the information filtration is the one of the historical Brownian motion, but it is also the one, as introduced in chapter 4, the one generated by the risky asset, or the one generated by the new Brownian motion W. Okay, in my situation, all these three sigma algebras and filtrations are the same here. And if I use the fact that this is equal to Vt over exponential RT, this one being equal to V capital T, so H over exponential R capital T. But from this, I obtain exactly this one. So here you have the value at any time, okay, of a strategy that replicate the contingent claim. And what is interesting is that, as you can see here, this value is independent of the choice of the replication portfolio, okay, from the martingale condition. So I also remind here that I have no arbitrage opportunities among P star admissible financial strategy, and just using the martingale property once again. And finally, okay, we have proposed to conclude the previous session the notion of price given by Black and Scholes and Merton, okay, in their seminal paper, that is the following. We call the price at time t of a contingent claim, okay, H, the value at time t of any replication portfolio associated to an admissible strategy, okay? First of all, I can say that I know that such a strategy exists in the Black and Scholes model because the model is complete. And what is more, I know that this price is unique because I have no arbitrage opportunities among P star admissible financial strategy. And that's why we work with P star admissible financial strategy, because we want the price to be unique, in fact. Okay, so the price exists from the completeness of the market, and the unicity is a consequence of the absence of arbitrage opportunity. Okay, and of course, by definition of a P star admissible strategy, if I denote by the price the value of this P star of any P star admissible strategy, I know that the actualized value of a P star admissible strategy is a martingale. And so for the price, exactly as I have done in the previous slide, I have this formula for the price of, okay, a contingent. Okay, so it means that in practice, okay, what are our objective in this course? Okay, we want to price and to hedge. Okay, price and hedge. For the price, okay, so if I give you a contingent claim, I want to price first and then to hedge. So to price according to this definition, okay, I have to compute this one. Okay, so I have to compute this one at any time. So we are going to see that at this stage, okay, I have just a theoretical expression in the form of a conditional expectation. I will see in a few seconds that, okay, in some situation, I am able to be a little bit more precise concerning this expression and even to be able to compute it explicitly, okay? And once I have obtained the price, okay, but the second step is to find, okay, theta 0 t theta, okay, that is P star admissible. and such that V capital T is equal to H. Okay? And I want to find it explicitly once again, because, okay, I know that there exists such a strategy because the market is P star complete, okay? And it's nice, huh? And it answers completely the question of replication or hedging in this situation, because, okay, if you want to sell a contingent claim, okay, what you will do, you will ask at time t equal to 0 for the price that you can deduce from this expression here. And then using this price, you are going to build the P star admissible strategy, okay? And you are able to do this strategy at any time because I know that this strategy is self-financed, okay? So it costs you nothing more than the initial price you ask for the beginning of the sale, okay? And I know that if I do my strategy, at the end, okay, I obtain exactly the payoff. That is exactly what I want to deliver if I am the seller of a European type option, okay, represented by a contingent claim. Okay, so if I have this one explicit, this one and this one explicit, okay, I answer perfectly in the Black-Scholes model to the question of the pricing and to the question of the hedging, okay? And at this stage, okay, the only thing I know from the definition 5.4.2 is that I have an expression for the price that is a theoretical expression in the form of a conditional expectation. I know the existence of a P star admissible financial strategy, and I want to be a little bit more explicit, okay, concerning the way to find these points concretely. And it's what we are going to do today. Okay. So we are going to consider particular families of contingent claims. Okay, so let me reduce a little slide here. Put it here. A contingent claim, a priori, is something, okay, in L2 of omega F capital T P P star. And I want it to be positive, okay? In this part, we are going to consider a very particular form for H. I want it to be of the form a function of S capital T, okay? So I have here a very particular form depending only on the final value of the risky asset. Okay, it's a very, very particular situation because a priori, a contingent claim is something, just something of this form here. Here I impose for H a very particular form that is just to be dependent on the final value. Okay, let me remind that in this original definition of a contingent claim, for example, I can have contingent claim of this form, for example, that are working. So I can take the maximum of, let's say, ST minus K plus for T belonging to 0 capital T. I have here a contingent claim in the sense of my definition, okay, here, but this contingent claim don't have this form because here you see that I depend on the whole trajectory of the risky asset, okay? It's not what I want in this part. I want to depend only on the final value. And we call this kind of product, okay, a product that is path independent. Path independent because it doesn't depend on the whole trajectory of the asset, only on its final value, contrary to what happened here, okay? And of course, so if I want to have my conditions here, I can impose F, let's say, to be positive, okay, and the expectation under P star of F of ST square to be finite, okay, in order to obtain this way H particular contingent claim. We are going to work with, okay? So we have example of such contingent claims. Typically, okay, if you take a call option or a put option or a digital option, this form, I am in this form. I have this form. Okay, I am a function of the final value with a function that is, okay, integrable. And keep in mind that I have no regularity on f. On f, I just have an integrability condition. So I have regularity in the sense of measurability, but I don't suppose for f to be continuous, to be differentiable and something like this, okay? So from the last definition we have seen together previously, okay, the definition of the price, that is this one here. If I give you a contingent claim from this definition here, you are able to say what is the price of this contingent claim. The price is given by this conditional expectation. Okay, so my price here, my price is given by, excuse me, the price is given by what? So in my situation here, the price is given by the conditional expectation under P star of exponential minus R capital T minus T. Here my H is F of S capital T given FTB. Okay. And here, what is nice is that since H has this very particular form, we are going, as usual, to decompose, okay, here, S capital T, in a part that is measurable with respect to FTB and a part that is independent. So in fact, I write S capital T to be ST, S capital T over ST. If I do this, I have here something that is FTB measurable, and here a part that is independent with respect to FTB. Okay, and I remind you that in this situation here, S capital T over ST may be written simply as exponential R minus sigma square over 2 capital T minus T multiply here by exponential sigma W capital T minus WT. I have this because keep in mind that I work under P star, so we are going to use the dynamic of the asset and the P star that is expressing the stochastic differential equation using the Browne motion under P star. So I have this. Okay, so I have a conditional expectation to compute. Okay, and to compute this conditional expectation, I remark here that I have a part that is FT measurable and a part that is independent. And it's a computation we have done several times together. Okay, that is to say, okay, we'll continue here, that I am able to say what is the conditional expectation in this situation. I know that Pt of H is a function. So here I have the time inside, okay, the conditional expectation T. So it will be a function of the time and of the FTB measurable part that is ST here, where Ft of X, it's something that I will call here the price function. Is equal to what? But it's equal to the expectation under P star of exponential minus R capital T minus T F of X S capital T over ST with, okay, I remove the conditional expectation, okay, and then with S capital T over ST, that is equal once again to exponential R minus sigma square over 2 capital T minus T plus sigma W capital T minus W small t. Okay, so I have an expectation to compute. The only source of randomness is this one here. But what I know is that this one can be written as the square root of capital T minus T N01 here under P star. Because W is a Brownian motion under P star, so I know that W capital T minus WT follows the N0 capital T minus T under P star. And it means that I can express this conditional expectation. So I continue my computation here. I can express this conditional or this expectation now, okay, as an integral. So it is exponential minus R capital T minus T integral. So with respect to the density of N01 of what? So of F of X. I have this term here that is exponential R minus sigma square over 2 capital T minus T plus sigma, okay, square root of capital T minus T, Y. And I have to multiply by the density of N01 because, okay, I know that the distribution of this one can be written this way. So it's exactly the expression that you have here. Okay, and of course, I remark that this expression is independent of the drift B. Okay, it depends only on the parameter sigma. Okay. Okay, so the price function, okay, may be explicited in this situation in the case where the payoff is the function of the final value of the risky asset. I can explicit it as an integral, okay? And if I want to go further in the computation, I need you to tell me what is this f. If I know what is this f, maybe I can compute explicitly this integral, okay? And it's what we are going to see later on. But at this stage, okay, we are going to see first that in fact this mapping capital F is regular, okay? Is regular in the sense that it depends on parameters that are, okay, two parameters that are the time and small x. And in fact, it is regular in t and in x, okay, in the following sense. So I write this, okay, it's what we are going to see here. So it's the lemma 551. So I won't do all the proof, but I want to show you the principle. So I am interested in capital F in this lemma, and I remind you that capital F, so I am interested here in this part. Capital F of Tx, I will copy it again. It's what? Exponential minus R capital T minus T, integral minus infinity plus infinity, F of X, exponential R minus sigma square over 2 capital T minus T plus sigma square root of capital T minus T Y. Okay, multiplied by the density of En01. So I said from lemma 551 that this mapping is of class C1 in the open interval 0 capital T. So for the first variable, that is the time, okay, I am C1 on the interval 0 capital T, open at capital T. And in the variable X, I am of class C2. Okay, I am twice differentiable with the derivative, the first and the second derivatives that are continuous. So just a remark first, okay? So here I see that for the dependence in the variable T, my interval is open at capital T here. And why it is open at capital T? It's because you have a square root here. And you know that the square root is not differentiable at 0. So if I take small t equal to capital T, okay, I have the square root at 0, explaining what, okay, at capital T, this function is not differentiable. Okay, well, it's my first remark. Second remark, I said that this lemma is remarkable because, okay, I said that under weak hypothesis. And what I mean by weak hypothesis, I mean that, okay, my payoff depends on F here. Okay? And a priori, at this stage, I have for F a single condition, that is, I want that this quantity is finite. So I have a measurability condition and an integrability condition through this relation here. I have no hypothesis, okay, concerning the fact that F is continuous, that F is differentiable, that F is twice differentiable. I don't know it, okay? So, and what is remarkable with this lemma is that, okay, in order to obtain the regularity of capital F, I don't need to have the regularity of small f in the sense of continuity, differentiability, or second differentiability. Okay, and I will try to, so I won't do the proof in all details, but I want just to show you that, okay, we can obtain, even if is not continuous or differentiable, I can obtain a capital F that is continuous or differentiable, okay? Okay, so when I see this, okay, I have a dependence in the time and in X. So here I have something that is regular in the time, and I have an integral depending on, okay, parameters that are T and X, okay, the variable of integration being Y here. In general, if I want to prove the regularity of an integral on parameters, okay, but I have to use Lebesgue type theorems, okay, and I have condition in order to ensure that an integral is regular, okay, on its parameters. But you see that if you want to apply Lebesgue regularity theorems, okay, in general, what you have in the integral has to be regular. And here it's not the case because a priori f is not regular in the sense of continuity, differentiability, and so on. I have no such an hypothesis for f. Okay, so what can I do? But in fact, the first thing I have to do is to do a change of variable. Because here you have a mapping that is very regular. It's a negative exponential. Okay, so you have a mapping that is of class C infinity. And the idea is to report, okay, the variable x and t here, not on f, because I don't know the regularity of f, and a priori it is not regular in the sense of continuity, differentiability, and so on, but to put this dependence on this part. And how to do? By doing a change of variable, in fact, simply. Okay, so I have y this way, okay, and I will define a new variable, z, that is equal to by what I have inside here. That is x exponential r minus sigma square over 2 capital T minus t plus sigma the square root of capital T minus ty. Okay, and this change of variable here means that y is equal to what? It's the logarithm of z over x, okay, minus r minus sigma square over 2 capital T minus t over sigma the square root of capital T minus T. And if I do this change of variable, and I will continue here, okay, this integral here becomes what? So I have the exponential minus R capital T minus T, that doesn't change. Okay, so Y belongs to all R. Z is equal to this one here. Okay, so Z will belongs to R plus, so it will be an integral from 0 to plus infinity here. Okay, Y belongs to R, but I have, okay, an exponential here. So I have this, okay, f of z, I have done the job this way, 1 over the square root of 2 pi exponential minus by y square. And what is the y? It's this one. So logarithm of z over x minus r minus sigma square over 2 capital T minus t over sigma the square root of capital T minus t, let's say dz here, and I have an over 2 here. Okay, and why it's nice here? Because it's nice because now the integral, what I have inside the integral, okay, is something that depends on classical mappings, okay? So studying the regularity of this integral in t in x is the same than studying the regularity of this integral. So maybe I have done a little mistake. So if I have this, okay, so I have an extra term maybe here because what is the y here? I have, okay, I have, yes, it's false what I have written because I have to take into account the fact that, okay, I have dy that is equal to what? Dy that is equal to 1 over, okay, x sigma the square root of capital T minus t. So z is equal to this one, okay, excuse me. So dy is equal to, I have a z here. Okay, dz. And so if I want to be precise, it's not a dz that I have here. It's simply a 1 over z square root of this one dz. Okay, I have this one. And I have here something that is regular in t and x. Okay, and so I see that through this change of variable, okay, I move the dependence on x and t from f to the density of my in01. And why I do this? Because I know that the density of my in01 is regular, okay? And now it means that in order to prove this lemma 551, instead of starting the problem with this form here, if I transform it into this kind of form, I will be able to use Lebesgue type theorem in order to do this, okay? And I can see that under very mild condition on the behavior on f in plus and minus infinity, I will be able to prove that this integral is regular in the sense of the fact that is C1 in the variable small t and of class C2 on R in the variable x, okay? So I don't have done the whole proof of this lemma, but the idea was to show you that even if f is not regular, capital F may be. Okay, and the idea is that I can prove it or have the intuition of it doing this change of variable in order to move the dependence, okay, of capital F in x and t, not through small f, but through this density function. Okay. So I suppose now that my function capital F is regular, okay, in the sense that I can compute the derivative with respect to the time, and I can compute the second derivative with respect to x. Excuse me, what I have done, yes. So it's not what I want to do here. So let me just once again, please, because I want just to put this one here. Okay. So I have this. So it's okay for the lemma 551. And now I have this proposition. Okay. So what is this proposition? So this proposition is really important from an intuitive point of view. And in fact, from a philosophical point of view in this kind of model. Okay, so what is the meaning of it? And we are going to prove it just after. You know that in the case where I have a payoff of this form, the price function is this one that is given by, in fact, a conditional expectation. Okay, it's a conditional expectation. So I have the price as a conditional expectation. And in particular, okay, we know that we have tools in probability in order to approximate expectation or conditional expectation. So I can write it this way, maybe approximated by Monte Carlo methods. And why I can do this here, okay, so keep in mind that we have seen together that f t of x here is equal to exponential minus r capital T minus t. Expectation and the p star of f x s capital T over st. Okay, and if I am able to compute this one, I will have this one at times more t, just plugging st in for the second variable. Okay, so here I have an expectation. Okay, so this conditional expectation using the Markov property of the process of the risky asset. Okay, as I have seen in the chapter 1. Okay, I can write it this way using the independence of the Brownian increments. Okay, and in fact here this expectation is in fact something that I have already written, but let's write it again. I write it this way, where J follows the N01 and the P star. And when I say, okay, that this price may be approximated by Monte Carlo method, I just say that in fact, this expectation may be approximated by Monte Carlo methods. Okay, so this one may be approximated using Monte Carlo methods, by just using the classical approximation. So, okay, I will include inside the exponential. And I can approximate this expectation using an average. Let's say this way. Of f of exactly the same thing. Plus sigma, the square root of capital T minus T, jk. Where G1, Gn are IID N01 and the P star. Okay? And in fact, to approximate the price function here, it's very, very basic. Because if I give you the model, so what you need to know, but you need to know in order to be able to do this explicitly, you need to know sigma, the volatility. And I will say at the end of the course, okay, how we can have an approximation of this sigma. And I need to give you the payoff function, f, okay? If I give you both, you are able to compute very basically, okay, this average generating an independent N01, something that is very easy to do with the computer. So intrinsically in the Black and Scholes models, price are expressed using conditional expectation. Conditional expectation that are just, in fact, expectation from the Markov property of the process, okay? And of course, as usual, I can approximate this expectation using Monte Carlo methods. So you have a purely probabilistic way in order to approximate the price of contingent claim in the Black and Scholes model, okay, using Monte Carlo methodology, okay? So it's the first point of view that may be nice, okay, in some situation when we are not able to compute this price explicitly. Okay, we have a way to approximate. And what is nice with Monte Carlo methods is that, okay, I know the way to use, okay, I know that using the central limit theorem, I have the possibility to build confidence interval to control the error I do, and so on and so on, okay? Now we are going to adopt another point of view. In the proposition 551 we are going to see now, okay, these propositions say that, in fact, the price function, that is this one, that I know to be an expectation that can be approximated by Monte Carlo methods, this price function may be also being expressed as a solution of a partial differential equation. A partial differential equation that is explicitly given by this one. And why this result is particularly interesting? Because, okay, but in the second semester, you have a course related to partial differential equation. Okay, and in fact, why you have a course on partial differential equation? But because in most of models, okay, the price function related to contingent claim may be expressed as solution of partial differential equation. And so if you are able to approximate numerically these solutions, you will have possibility to approximate numerically the price of a contingent claim in the Black and Scholes model. So what is very, very nice, okay, is that I have two very different points of view on the same question. Same question, that is how to approximate prices, okay, in the Black and Scholes model when I am not able to compute them explicitly. I have two ways to do, using purely probabilistic methods from Monte Carlo methodology, or, okay, using tools from analysis, okay, approximating solutions of partial differential equations. Okay, so two very different point of views on the same question. Okay, so let's prove this proposition 551. Okay. So I remind you that the price of my contingent claim. I write everything once again. Is given by this one. And it's equal to FT of ST. Okay? In particular, okay, we know that P T H tilde, okay, we know that this is by definition of the price, okay, is a martingale. Mind that I do the proof of this one. Okay, and what is PTH tilde? It is just FT of ST divided by exponential RT. And in fact, we are going to write this expression not as a function of ST, but as a function of ST tilde. And why I do this? Because I know that under P star, I know that I have this, d of ST is equal to R ST dt plus sigma ST dWt. And from the integration by part formula, d of ST tilde, I know that d of ST tilde is by definition of P star, that is an equivalent martingale measure, a martingale, okay, and I obtain this representation for this martingale. So I have a very easy stochastic differential equation for this one. The one for ST is a little bit more complicated. The one for ST tilde is simpler, okay? And that's why instead of having a function of ST, here we are going to write this as a function of ST tilde. So it's a definition. I define this quantity as F tilde of T and ST tilde. And in particular, it means from what I have written that it means that, okay, F tilde of T x here is in fact simply equal to what? So I just have to plug inside here. I use the fact that ST tilde is equal to ST over exponential RT. So I have here this one that is equal to exponential minus RT F of T exponential RT x. Okay, so I define this mapping, and in this way ft tilde of T st tilde is equal to, I impose this one in order to have that f tilde of T st tilde is equal, if I do it this way, is equal to P T H tilde. So you have this one that is a martingale under P star. Okay, so what I have here, I have this ft tilde T st tilde. Mapping depending on T and on st tilde. What can I do with this regular mapping depending on T and st tilde? I know the Ito decomposition of st tilde. And a good idea will be to apply the Ito formula to this mapping here, okay? In the sense that, okay, Ito formula give me so the Ito formula give me the following, that d of P T H tilde is equal to what? Is equal to d of F tilde T ST tilde. And by the Ito formula, I can express this quantity here. It's equal to D of F tilde over dx T ST tilde D of ST tilde plus 1/2 the second derivative of F tilde with respect to x T, excuse me, T ST tilde multiplied by what? The square of the term that is in front of dWt in the Ito decomposition of ST tilde. So it is sigma square ST tilde dt plus, plus an extra term because I have a function that also depends on time here. So that is d of f tilde over dt t of st tilde dt. So the Ito formula gives me this expression for the Ito differential of the price of my contingent. Okay, so I have this. Okay, but keep in mind that the price of a contingent claim is defined as the value of at any time of what? A P star attainable financial strategy. Okay, the price at any time is equal to the value of a portfolio associated to a P star attainable financial strategy. And it implies, okay, that we have the following equality. So this one, this quantity here is also equal to the following one. By the self-finance condition, I know that a P-star admissible financial strategy is self-financed. Okay, since it is in finance, we have that the Ito differential of the value is equal to theta T D of ST tilde. I have this, okay? And it's a consequence, just let me remind, okay, it's the proposition. So what I have here, so just the self-financed condition. So I repeat, because it's, in fact, it's the main point of the proof. After it's just computation, okay? So let's come back to what I have done previously. Yes, it's this one, no, yes. So the price of a contingent claim is the value at any time of a replication portfolio, okay? So if I take theta 0, theta t, okay, that fulfills V capital T is equal to H. What we call the price is equal to VT. But P star admissible implies self-financed. And so I have D of VT tilde that is equal to theta T D of ST tilde. But this D of DT tilde is just D of PTH tilde by definition of the price, okay? So I have this stochastic differential equation for the actualized price, okay, from the fact that the price is given by the value of a P star attainable financial strategy that is in particular self-financed. So if I come back to my problem here, I have these things, okay? So I have two stochastic differential equations that are fulfilled by the actualized value of the price. And so by the unicity of the Ito decomposition, unicity of Ito decomposition, I can deduce two things. So here I see that I don't have part in dt. If I don't have part in dt, it means that the part in dt is equal to 0. So first, 1/2 the second derivative of f tilde over dx square t st tilde sigma square st tilde plus d of f tilde over dt st tilde. This one is 0. The part in dt here is 0 because I don't have a part in dt here. Okay, so the part in dt is 0. Second equality I can deduce from the equality between these two Ito decomposition because I have here d of st tilde, here d of st tilde, and so theta of t, that is my quantity of risky asset in my replication portfolio, has to be equal to this quantity here. D of f tilde over dx t of st tilde. Okay? And in fact, now the proof is finished. The only thing I have to do now, okay, is to compute. And I will have to compute what? So keep in mind what I have obtained. So I repeat my reasoning. Okay, I express the actualized price of my contingent claim, okay, using the function f tilde of t and st tilde. I say that here, okay, I have the value of a self-finance strategy by definition of what is the price, okay, the value of any replication portfolio associated to a P-star admissible financial strategy. So I obtain this. And also using the Ito formula, since this one is a regular function of T of st tilde by lemma 551, the Ito formula may be used because I have this lemma here. I apply the Ito formula and then I make these two parts equal. And from the unicity of the Ito decomposition, I know that here I don't have a part in dt, so this part in dt has to be equal to 0, implying that this one is equal to 0. And this part has to be equal to this one, implying that theta of t is equal to this one. So I have two equations here. Here, a partial differential equation, but for f tilde, and here the expression of the quantity of risky asset to put in the hedging portfolio, that is, okay, the derivative of f tilde with respect to x at t and st tilde, from which I have to deduce these two. And in fact, from this one, we are going to deduce this one. And from this one, we are going to deduce this one. Okay? And why we are going, how we are going to pass from f tilde to f here. I have things involving f tilde and I want to obtain things involving f by just using this. F tilde is equal to this one. So I am able to express the partial derivatives of f tilde in terms of the one of f. Okay, so it's exactly what we are going to do now. So I duplicate this slide here because I want to keep what I have written here. So I keep this one. I will erase most of the things. Okay, so I erase this one. That is the main argument. And in fact, okay, the strong argument of this one. I just keep for the moment this one. I can erase this and this. And I will just copy what I have written here. So f tilde of tx is equal to what? Exponential minus r t f t exponential r t of x. And so I can erase this part. Okay, so now what I have? I have this one and this one, and I want to express these two using the partial derivative of f instead of the partial derivative of f tilde. So let's do the job. So for the derivative with respect to x, I said that d of f tilde tx over dx is equal to what? So I have to compute the derivative of this one with respect to x. Very nice. Exponential minus rt. It's df over dx t exponential rtx multiplied by the derivative of what I have inside here, that is exponential rt. So I have simplification between this term and this term. And at the end, I obtain from this one that d of ft tilde over dx of t st tilde is equal to what? Is equal to df over dx of the time t and of exponential rt multiplied by st tilde, that is just equal to st. And this equality and this one imply what I have here. In the Black-Scholes model, the quantity of risky assets to put in the aging portfolio is just the derivative of the price function, okay, with respect to the second variable. Okay, so I have done half of the job here. I have proved that theta of t, that is equal to this one, from my little computation here, is equal to df over dx tst, where f is the price function. Okay. So it's the first point. So second point, I have to do the same for the other partial derivatives involved in my relation. So I have this one and this one. So let's do it for the second derivative here. Because what is the second derivative? The second derivative is just the derivative of the first. What is this one? But I start from this one. I have to compute the derivative of this one. And once again, okay, I obtain by the differentiation of compound function, this one. I have this one. And so from which I deduce that, okay, d2f tilde over dx square t st tilde is equal to what? Is equal to d2f over dx square t st tilde multiplied by exponential rt, that is equal to st, and multiplied by exponential rt. So I have exactly this one. Okay. So I have this one. That is something that I can write in yellow here, and that I will plug here. And you see that if you plug this one here, you start to see by this part here, in fact. Okay. So finally, I have to compute the derivative of f tilde with respect to the time. And here it's a little bit more complicated because you have time here, here, and here. Okay. So when I compute d f tilde of tx with respect to the time, so I have first a product u time v. So it's u prime v. So u prime minus r exponential minus rt u prime v plus u v prime. So derivative of this one with respect to t. I have two terms here because I have t here and t here. So it is df over dt t exponential r tx plus df over dx t exponential r tx multiplied by the derivative with respect to the time of this one, that is r exponential r t x. Okay, so I just check in my notes, okay, if I'm with this, okay, a priori it's okay. 2 plus exponential minus rt plus r exponential r. Okay, so from which I deduce that d of ft tilde over dt t of st tilde is equal to what? So it is equal to this term here, so that is minus r exponential minus rt f t and st, because exponential rt multiplied by st tilde is equal to st, plus this term here, that is exponential minus rt df over dt t st, and plus what? Plus what? Plus what? So I have here this term. Okay, so I have simplification between this one and this one. If I plug st tilde here, I can write it this way, plus r df over dx t st multiplied by, so I have the r that is here, the exponential that simplify, and it remains the x where I plug st tilde. So I have st tilde that I can write as st exponential minus rt. And this quantity here may be plugged here. And if I summarize, if you replace the yellow part by this one here, if you replace the red part by this one, if I don't have done errors of computation, you will recover, so this part and this part come from the red one, okay? Okay, so at home, it's a good exercise to plug inside what I have done, the computation I have done, and check by yourself that you obtain exactly this one, okay? So you have here the partial differential equation that is fulfilled by the price function in the Black and Scholes model. And I repeat that it gives you another point of view on the price function that is, okay, not a probabilistic point of view that comes from the fact that this price function is a conditional expectation, but that comes from analysis, having in mind that this price function is solution of partial differential equation. Okay, so I have this. So let me just conclude by one thing, okay, because I have here a little thing that I have missed. So you have an equation, okay, and you know that in general, okay, you can, if you want the unicity in the solution of an equation, okay, you need to impose an initial or a terminal condition here. But let me just duplicate the things, okay. Let's do it here. I erase all these computations, and that we can recover in the lectures note, okay. Yeah, I just want to conclude with this point here, this part. I remind you that f t of x, okay, is equal to what? Is equal to exponential minus r capital T minus t, the expectation under P star of f of if x s capital T over st. Okay. So what happened? Okay, so I have the price function, and I said that for small t equal to capital T, what I have is simply the fact that, so here I have exponential of 0 because capital T is equal to small t here, and here I have simplification between this one. So I have simply f of x. Okay. So I have this terminal condition, and in this way you will have to correct the fact that here it's not h, it's f. Okay, it's f. F capital T of x is equal to f. So here it's an f, not an h. Okay. Okay, so I can express here, in the case where the contingent claim has the form of a function of s capital T, I can express the price function as a solution of a partial differential equation, a partial differential equation that I called the Black and Scholes PDE. Okay, so I have this. So let's continue. So now, okay, so the only thing that I have proposed to you at this stage, okay, is another point of view on the way to consider the price function in the case where the contingent claim is a function of the terminal value of the asset. Okay. Now we are going to be a little bit more precise, proving, okay, the so-called Black and Scholes formula. So what is the Black and Scholes formula? So the Black and Scholes formula just tell you that in the case of a call or a put, it's equivalent, but for a call option. So here I am in the case of a call option. Okay, that is my contingent claim is equal to S capital T minus K plus. So it is exactly of the previous form, f of the terminal value of the asset, where f of x is just equal to x minus K plus. Okay? And the idea is to compute explicitly the price. So I will denote the price by C here. So I define the price of a call, CT, so the price of a call at time t, its definition or notation, that is PTH. And I know what is this one, okay? It is equal, according to what I have done previously, to FT of ST, where, okay, FT of X is equal, so it's something that I have written several ways, but let's write it again and again. So it is exactly this one, okay? And now what I want to do here is to be able to compute this explicitly, okay? So I have this expectation. We have seen previously that this expectation is the solution of a partial differential equation, but in the case of a call, and only in this case, it works for a European call option, I am able to do the computation explicitly here. So my objective is to compute, okay, this thing here. My objective is to compute this thing. So let's do the job, okay? So it's not that complicated. We just have to be methodic, okay? So what is this one? So I can express it as an integral, as I have previously done. So let's write it this way. Okay. So what is S capital T over ST? I can write it this way. So it's exponential R minus sigma square over 2 capital T minus T plus sigma. Okay. So it's W capital T minus WT. That is the square root of capital T minus T n 0, 1. So I can write it this way as I have previously done. Minus K plus, okay, and I multiply by the density of n01. Okay, dy. I have exactly this. Okay, so we are going to make enter this one here because if I do this, I will have some simplification because here you see that you have exponential R capital T minus T that I can simplify with this one. So I can write it as integral minus infinity plus infinity of x exponential minus sigma square over 2 capital T minus T plus sigma the square root of capital T minus T y minus K multiplied by this one. I have the right to make this one enter here because this one is strictly positive. Huh? I have something that is strictly positive, so I can make it enter in the plus mapping here. Okay, this one, okay, plus 1 over the square root of 2 pi exponential minus y squared over 2 dy. Okay, so I have the plus function. You know that the plus function is 0 if this term is negative and identity otherwise. So I have to be interested when this one is positive or not inside. And I said that to say that x exponential minus sigma square over 2 capital T minus T plus sigma square root of capital T minus Ty minus K exponential minus R capital T minus T. When this one is positive, it's positive if and only if. So we are going to express it, okay, as a condition on Y. Okay, so you put this one here, you divide by X, you take the logarithm, and then you plus this one, and you divide by sigma the square root of capital T minus T, and you obtain, using my notation here, okay, you obtain that this one is equivalent to saying that Y is greater than minus d2 tx. d2 of tx being given by this expression here. So do it by yourself at home, okay? I repeat that you make this one pass here with a plus, you divide by x, you do plus, you take the logarithm, you do plus of this one and divide by sigma the square root of capital T minus T to obtain y greater than someone, and this someone is none other than the minus d2 defined here, okay? So it means that if I continue my computation, I can express f t x as the integral. So when I am not 0, when I am greater than minus d2. Okay, for y of the same thing. So I copy the same thing, that is x exponential minus y squared over 2 capital T minus T plus sigma the square root of capital T minus T y minus K exponential minus R capital T minus T. I close my parentheses and I have a minus here, okay, and multiply by the density of my N01. Okay, so I have this. Okay, so as you see here, I want to express the price of a call as a function of ST and time, of course, but where capital N here is the distribution function of N01. Okay, so I want to express these things, okay, using the distribution function of N01. So the first thing we are going to do here is to change the variable in order to make this integral to be from minus infinity to some one. Okay, because I want to make appear distribution function of N01. So I can write it this way. So I do this change of variable. Okay, I change y into minus y here. I do a change of variable. If I do this, okay, it's integral from minus infinity to d2 of tx, okay, of two terms that are x exponential minus sigma square over 2 capital T minus t plus sigma square root of capital T minus t y minus k exponential minus r capital T minus t multiplied by the density of the N01. And excuse me, here, since I have changed y into minus y, I have a minus here, not a plus. Okay. So I have this one. Okay. I have two terms, in fact, here, because I have a minus. I have two terms that are, in fact, not that difficult to handle. So let's write these two terms. I have a first term that is integral minus infinity d2 tx of what? Of x exponential of minus sigma square over 2t minus t minus, so it's this term here that I will write. This one multiplied by this one. And then I will continue, and I have minus by the other one, that is this one multiplied by this one, that is minus k exponential minus r capital T minus t integral minus infinity of d2 of what? The density of my N01. And this one, with the minus included, is minus k exponential minus r capital T minus t. And here you have simply the distribution function of the Gaussian N01 at the point D2. And you see that this term here is exactly the term that you've seen appear here. Okay, so I have the second part of the equation. If I come back to my first term, so I have this one, okay. I have the square root of 2, excuse me, I will change my color. I have the square root of 2 pi. And I have this exponential here. And in fact, I see that in this exponential, I can make appear a perfect square. In fact, I can make appear a perfect square. It is exponential of what? Of minus 1/2 y square minus sigma the square root of capital T minus t. Oh, excuse me, square here, dy. Why? Because if I consider this term, and this term, okay, they can be regrouped into this way. Okay, I have exponential y square over 2, that is this term. I have the double product, okay, that give me exactly, so there is a plus here. The double product that give me exactly this term here. And okay, this term that is the square of this one divided by 2. Okay, so I regroup these 3 terms in the exponential into a perfect square this way. Okay, and now, but it's not complicated to compute this one because I can just do a change of variable here. This one, changing y into y plus square root sigma square root of capital T minus T. I do this change of variable in order to put this one simpler. I obtain an integral here that is the integral, so from minus infinity to, so if y starts from d2, the new one starts from d2 plus sigma the square root of capital T minus T, and I have x over the square root of 2 pi exponential minus y square over 2 dy. But what is this term here? I can remove the x, okay, from this because it doesn't depend on y, and then I have the integral between minus infinity and this term of the n01 density. So I have n of d2 tx plus sigma the square root of capital T minus T. But what is this one? It is x d2 plus sigma the square root of capital T minus T. So this one plus sigma the square root of capital T minus T just give me d1. In fact, I have here n d1 of tx. I repeat that I have just used here the fact that d2 of tx plus sigma the square root of capital T minus T with my notations here is equal to d1 to tx. And this relation here is plugged here. And so I have x n d1 tx, x n d1 tx, and this term here is exactly the one I have obtained here. And you see that it's not that complicated to obtain heat, okay? So the Black and Scholes formula, that means the price of a call option in the Black and Scholes model. The price of a call option in the Black and Scholes model, okay? So 2 remarks concerning this. So I have done this for the moment. This proposition also gives me the composition of the aging portfolio. Okay, the composition of the aging portfolio. So what is this aging portfolio? So I know that ST is equal to, CT is equal to ST n d1 t ST minus K exponential minus R capital T minus T I'll just wait 5 seconds, please. I have to do something at home. Okay, so let's come back to the slide. Okay. So I have this, okay. That is the price of a call option that I have proved previously with the Black and Scholes formula. And I have here n d2 t of st. And this is equal to capital F t of st, the price function. Okay, so if I am interested in if I am interested in the composition of the aging portfolio, I know from the previous proposition, okay, from the previous proposition, I know that the quantity of risky asset to put in the aging portfolio is just the derivative of the price function with respect to X, okay? So for the aging portfolio, or the replication portfolio, it's the same thing. So it's theta 0 t, theta t. Okay, I know that theta of t is equal to df over dx t st. And in fact, what is CT? CT is equal to the quantity of non-risky asset multiplied by the value of the non-risky asset plus theta t st, implying from this one that theta 0 t is equal to, I can write it this way, CT minus theta t st exponential minus RT. So if I want to obtain theta t, and so as a byproduct theta 0 t, okay, but then I can, I have to compute the derivative of f with respect to x, okay? So let's do the job. So here I have f of tx that is equal to what? Okay, is equal to x n d1 tx minus k exponential minus r capital T minus t and d2 tx. And I also remind you that I have a link between d1 and d2 in the sense that, for example, d2 of tx is equal to what? So it's d1 minus sigma square, the square root of capital T minus t. Okay, so let's duplicate this part. And just keep what I have written at the end. So I erase the beginning. So if I want to obtain theta, I am interested in df over dx of dx that I can obtain from this one. Okay, so here I have x here and here, so it is u prime v plus u v prime. So what is v prime here? It is n prime d1 tx d1 prime tx. So I have computed the derivative of this part here, and minus the derivative of this one, that is minus k exponential minus r capital T minus t. The derivative of this one, that is n prime d2 tx, okay, d2 prime of tx. Okay, so I have this. Okay, so I can compute a little more. Okay, so keep in mind first that here, the derivative of the distribution function is just by the density function. the derivative of capital N, that is the distribution function, is just the density function of my N01. And I have also that D2 is equal to D1 minus sigma square square root of capital T minus T. If I compute D1 prime of Tx, the derivative of D1 with respect to x, it's this one that is very easy to obtain, and I obtain 1 over x sigma the square root of capital T minus T. And according to this formula, it's the same as the derivative of D2. Okay? So using all these things, I have N D1 Tx, that is in fact the term I want to obtain, plus, okay, so what I can put into factor by the d prime because they are the same here, okay, so I can write it this way, it's 1 over x sigma the square root of capital T minus T, because the two derivatives are equal, and then I have a term that is x, okay, n prime of d1 x n prime of d1, that is 1 over the square root of 2 pi exponential minus d1 square over 2, that is this part here, and minus k exponential minus r capital T minus T. And I have, okay, the derivative of capital N, that is the density at D2, with D2 that is equal to this one. Okay, so it is over the square root of 2 pi exponential minus, so D2, that is, let's write it this way, D1, okay, minus sigma square root, oh, excuse me, it's the sigma that you have here. It's not, so minus sigma the square root of capital T minus T. So let's do the job here. D1 of D1 minus sigma square root of capital T minus T square over 2, and I close the bracket here. Okay, so I won't do the computation because I don't have too much place here, but at home you can prove that this one is simply equal to 0. Okay, so you can do the computation. You have D1 given by this expression here. Okay, so you replace and you will obtain exactly what you want. That is that this term here is equal to 0 to recover at the end that df over dx of tx is equal to n d1 tx, and so that theta t is equal to n d1 t of st. Okay, and I can deduce, so you have here, I can write this one as st, in fact, theta t, okay, minus this term. And in fact, I can see easily that the related theta 0, okay, the related theta 0 is simply given by this expression here. Okay, so I have here not only the price of a call option, but I have also the quantity of risky asset I have to put in the aging portfolio, and as a byproduct, the quantity of non-risky asset I have to put in the aging portfolio. And keep in mind that this is true for a European call option. Let me remind you that if I have the job for the call, I have the job for the put, because you have the put call parity that tell you that the price of a put at time t plus the price of the risky asset is equal to the price of the call plus k exponential minus r capital T minus t. And it means that if you replace the CT you obtain here in this proposition in this expression, you will be able to obtain a nice formula for PT. Okay? So you have the result for the call here, and as a byproduct, we have the result for a put using the put call, the call put parity. Okay. So this is the Black and Scholes formula that gives you a closed form expression in order to obtain the price of a call or a put European option in the Black and Scholes model and the corresponding quantities of risky and non-risky assets to put in the replication portfolio. Okay. So let me finish with a little definition. That is what we call the Greeks in general. Okay. So what are the Greeks? So the Greeks are in fact, so they call the Greeks because we use in general, okay, Greeks later in order to define them or to denote them. Okay. So they are the derivatives of the price function with respect to quantities of interest. Okay. We call delta, okay, the derivative of the price function with respect to the second variable. Okay, it's what we call the delta. We denote by gamma the second derivative of the price function with respect to the second variable at t and st. Theta is the derivative of the price function with respect to the time. Rho is the derivative of the price with respect to the interest rate. And vega, that is not a Greek letter, but that is also called a Greek, is the derivative of the price function with respect to the volatility. Okay, so just a remark concerning, okay, the intuition behind the financial intuition behind some of them. First, this one has a strong financial interpretation because it's the quantity of risky asset to put in the aging portfolio. Okay, so this quantity, that is the derivative of the price function with respect to the second variable. We have seen two propositions ago that it was exactly the quantity of risky asset to put in the aging portfolio. So something that is really important. So let me just give to you the interpretation of the second derivative that we call the gamma. Okay. So I am at time t equal to 0. And let's say the maturity of a financial product here, delta. In the framework of the Black and Scholes model, okay, I know that from a theoretical point of view, it is possible to price and to age contingent claim because the market is complete, okay? So what you do in practice? In practice, okay, if you want to use the Black and Scholes model to have a perfect hedging, okay, you have to readjust the portfolio at any time because you have a continuous time trading. Okay, so at any time t, you have to be sure that the quantity of risky and non-risky assets in your portfolio is exactly the one given by the Black and Scholes model. And typically, if I am in the case of the call option, I have a closed form expression for the theta and a closed form expression for the theta 0. But in practice, okay, it's not what we do. Because in practice, okay, even if I don't have supposed this before, in practice, you have transaction cost, meaning that if you want to readjust your portfolio at any time, it will cost you a lot, because to buy and sell assets, okay, will cost you some amount of money. So in general, if you want to hedge in real life, you have to consider a discretization of your period, okay, and say that, okay, I will readjust my portfolio, okay, at these discretization dates, okay, because I can't do the things in continuous time. So let's try to do them, okay, in a discrete way. And this is the interest of the gamma here, because what is the gamma? It's the derivative, the second derivative of the price function. So it's the derivative of the first derivative. And gamma measures the sensitivity of the delta to the variation of the risky asset, meaning that it's the sensitivity of the quantity of risky asset to put in the engine portfolio with respect to change in the underlying. So in practice, what I do, suppose that you are here, okay? So you can build at time t equal to 0 your portfolio. You have theta 0, 0, theta 0 that are given, okay, by the framework given by Black and Scholes, okay? And now the question is, okay, how long I can stay at this position if I want to have an age that is not that bad. I know that in the Black and Scholes model, I have to do a continuous time hedging, but I can't do this in practice. So how long I have to wait before to change my portfolio in order not to be very far from the theoretical edge? And in fact, this answer this question may be answered by the value of the gamma, because suppose that at time t equal to 0, you have a very small gamma. A very small gamma will mean that, okay, the quantities here are not very sensitive to changes in the underlying, meaning that you can wait a little time here, because even if you have some change in the risky asset, okay, it won't affect too much the composition of your aging portfolio. Suppose that you are in another situation. If the gamma is big, it means that you are here very sensitive to changes, okay, for the risky asset. And so in this situation, it will be better for you to readjust your portfolio, okay, at a time period that is shorter, okay? So in fact, the gamma will be a tool that will allow you to decide whether or not you have to wait a long or a short time before to readjust your aging portfolio, okay? So this one is related, as I have explained here, to, let's say, the hedging frequency. Another quantity that is very important is the vega. Vega is the sensitivity of the price function to the volatility. And keep in mind that the volatility is the only unknown parameter in your model. The only unknown parameter. So if you have a small vega, it means that, okay, the price that you will obtain will be that dependent on this sigma. So you can try to estimate it or obtain it the way you want, but you can do this roughly, okay? Because the price is not that dependent on the value of this unknown parameter. Contrary to the case where if vega is very big, you have to be very careful in the sigma you plug in the formula, because it will change a lot the value of your price. Okay, so in some sense, the Vega is a quantity that gives you some indication concerning the way you have to be careful to estimate or obtain the value of the unknown parameter in the Black-Scholes model. Okay? And then for the two other one, okay, it's just, okay, quantities of interest, okay? So theta is related to what we call the time value of an option, okay? And rho, just say that be careful in the interest rate you enter because it can change, okay, the value of your price, okay? But in general, in real life problem, okay, the choice of R is not that unclear, okay? So the delta, the quantity of risky asset to put in the aging portfolio, gamma, the variation or the sensitivity of this delta with respect to the underlying, giving to you indication concerning the frequency at which you are going to readjust your aging portfolio. And Vega, okay, a quantity that will give you some indication concerning, okay, the way you have to estimate the volatility, okay? And in the case of the Black-Scholes model, okay, for call and put option, so here you have Greeks at time t equal to 0. I have given to you the formula for the Greeks in the Black-Scholes model, okay, at time t equal to 0. So for time t here, you just have to change capital T into capital T minus T using the Markov property and the homogeneity of the Black-Scholes equation. Okay, so you have closed form expression for the Greeks in the case of the Black-Scholes model, okay? And typically, you see that the delta and the Vega, okay, are more or less the same, yes, excuse me, not the delta, the gamma and the Vega are equal up to a constant, okay, are equal up to a constant, in fact. Okay, so to conclude, and in fact, to conclude the course, and to make, in fact, open question concerning the course of the second semester. So you have, okay, well, let's open several questions. So concerning the Greeks, okay, we have seen together that we have closed form expression for call and put in Black-Scholes model. Okay. A natural question is how to obtain them. Okay. For the first step will be for more general contingent claims. And why this question is important? Because I have telling you that some Greeks, okay, have a strong financial interpretation. The delta is the quantity of risky asset to put in the aging portfolio. Gamma is related to the aging frequency, and Vega is related to, okay, the estimation of the volatility sigma. Okay, so for contingent claim in general, okay, it's interesting to have access to this quantity. In this type of model, prices are given by expectation or conditional expectation. And so the Greeks are derivatives of expectations. So it means that if I want to approximate the Greeks, contrary to the price where I can approximate it, for example, using Monte Carlo methods, I have for the Greeks to approximate an expectation and then approximate its derivatives. So I have two sources of approximation that may be cumbersome to handle. Okay? And in my course of the second semester, okay, I will answer this question. Semester 2. So it's what I will do. I will propose you, okay, some tools in order to compute in an efficient way. So not necessarily in the Black-Scholes model, but also for more general models, the way to compute the Greeks, okay, in an efficient way to overcome the problem of the double, let's say, approximation. Okay. You have another problem, that is the choice of sigma. Okay. So let's discuss this point because it's a very interesting point in the Black-Scholes model. So remind that in the Black-Scholes model, the historical dynamic is given by this one that depends on the drift and on the volatility. In particular, ST, okay, is given by x0 exponential b minus sigma square over 2 capital T minus T plus sigma bt. Okay? Okay, so I want to have a weight in order to estimate this sigma. Okay? So suppose that you are at time t equal to 0 here, and that you want to price, okay, a financial product with maturity at capital T to fix the ID. Okay, let's say that it may be a call or a put option. And in general, okay, if you want to forecast the price of a financial product, you have to fix the parameter of interest in the model. And I know that in the case of the Black-Scholes model, the only parameter of interest in order to price is the volatility, because B disappears in the pricing problem, okay? And how to do this in general? But we are going to try to estimate using, okay, let's say data in the past. Okay, so the forecast period, that is what I want to do in the future. And here you have, okay, historical data here that are available. That is the past. Okay, so I can consider a discretization of this period here, having this kind of points here. I consider a discretization of step size t tilde over n. Okay, if I do this, I can consider the log returns on this period here. Okay, so if I consider the log returns, so let's consider the log returns that are log of what? S minus t tilde minus n minus 1 over n t tilde until the logarithm of S0 over S minus t tilde here over n. So I have log returns of my, so I can write this one as y1. And I have how many of them I have? I have exactly n. I have this one, okay? I have my capital N log returns that I can build from my historical data here, okay? What can I say? I can say from the Black and Scholes hypothesis that y1, yn are IID. IID what? IID Gaussian, because it's the logarithm of exponential of something that is a Gaussian. And I can find explicitly what is the distribution of these log returns, okay? These log returns have a distribution that is a Gaussian distribution with mean b minus sigma square over 2 t tilde over n, and a variance that is sigma square t tilde over n. In particular, here, sigma is related to the variance of the log return up to this constant here, okay? Sigma is related to the variance of the log returns that are IID random variables. So I know from statistics that I can approximate, so sigma, the volatility here, may be approximated using the empirical variance this way. It's the square root of, well, I write the formula. So from I equal to 1 to n of yi minus the sample mean square. Okay, it's the empirical variance. You have the unbiased empirical variance. So it means that from observations of log returns of your process in the past, you can, okay, estimate the volatility from these log returns. Okay, so it's one way to obtain the volatility. Okay, but it's not the only way in the Black and Scholes model. Another way is the following. In this table here, you see that the vega, that is the sensitivity of the coal price with respect to the volatility, is something that is strictly positive. Okay, is something that is strictly positive. So I have that the vega at time t, that is the derivative of the price function with respect to the volatility, is strictly positive, okay, for a call. And so the mapping that associates to sigma the price of a call option at time t, okay, with vol sigma is strictly increasing. And in fact, is a bijection from R plus into R plus. Why this fact is interesting? This fact is interesting because in the market, okay, sometimes you can observe the price of some call option. If you observe in a market the price, let's write it this way, CT ops of a call option. But you can find sigma solving, for example, CT sigma is equal to CT ops. You know that you have a unique solution to this equation from my preceding argument, okay? And so you can plug the good sigma and try to find it explicitly in order to cope with the observed market price for a call option, okay? And the previous approach here is called estimation. The second approach here is called calibration. And a priori, in a perfect world, okay, but the two approaches, the two strategies here to have sigma should give rise to more or less the same thing for the obtained sigma. And in practice, we see that it's not what we obtain. And it's not what we obtain. And the fact that we have a difference between these two approaches, okay, is a major drawback, okay, in the Black and Scholes model. Because the Black and Scholes model is based on a very strong hypothesis that is to depend on a single parameter, that is the volatility sigma, that is constant, okay, over time in particular, okay? But that's also to be constant for any call option, for any maturity and any strike. And in fact, it's not what we observe in the market. Okay, so estimation and calibration in the Black and Scholes model give rise to very different things. And in particular, it underlines the fact that the sigma I obtain here will change if I change, okay, the characteristic of the call option I observe, okay? So it is in relation with two courses that you are going to do in the second semester. You will have a course, if you take it, on stochastic volatility. So in some sense, sigma no more constant. So it is extension of the Black and Scholes framework in order to overcome the problem of why calibration and estimation don't give the same thing in the Black and Scholes model, okay? But because I have to extend the model, in fact, because the Black and Scholes dynamic is too restrictive if I want to be able to replicate all the observed call option prices present in the market, okay? So it's the first course here, and the second course that will be related to calibration. Oh, excuse me. In fact, these two scores will be the same if I remind calibration. Okay? Stochastic volatility and calibration. And the last thing that I can say, okay, in order to conclude, is that we have seen that for the price, you can see it in two different ways, okay, as an expectation, let's say. Expectation. Here, as a solution of a partial differential equation. Here, you are in the domain of probability. Here, you are in the domain of classical analysis. And that's why in the semester 2, you have a course that is proposed on PDE here, okay? In order to obtain prices, okay, as solution of partial differential equation, and you have, okay, a whole course that is devoted to how to approximate solutions of partial differential equation. And from this master, it has an interest in the fact that approximating this solution will be another way to approximate, okay, prices in the financial model we are interested in. Okay, so see you for the next session that will be devoted to the correction of the exam of the previous year. Bye bye.